Hello, everyone, and welcome to our exciting panel. We're honored to have some incredible panelists joining us today, all leaders in their respective subfields. We're looking forward to a thought-provoking and invigorating discussion here today. There we go. So in 2021, as we're paving the way towards scalable quantum computing, our focus is on solving problems which are the most immediate roadblocks, significantly improving gate fidelities, producing increasingly complex QPUs, and building tools for error mitigation. In the NISQ era of today, our bottlenecks are quite fundamental. With this panel, however, we're aiming at the future with an attempt to envision what the quantum computers of 2050 will look like. With us, give our panelists free rein to think long-term and remove the three main roadblocks facing their research today across various qubit platforms. We will focus on answering the following questions. What is the next set of big challenges for the quantum research community? And how should this affect the work being done today? What will the ideal future quantum computer look like? What hardware will it contain? And which problems will it be able to solve? And what will become the new problems? What kind of architecture will be expected? And what would the role of quantum control be at that point? Now, while our panelists don't really require it, I will first start with a small introduction of everyone joining us today. First, we have Prof. Scott Aaronson. He is a David J. Burton Centennial Professor of Computer Science at the University of Texas at Austin. Aaronson's research in theoretical computer science is focused mainly on the capabilities and limits of quantum computers. His first book, Quantum Computing Since Democritus, was published in 2013 by Cambridge University Press. He received the National Science Foundation's Alan T. Waterman Award and the United States PCASE Award, amongst many others. We have Professor Rainer Blatt. He is a professor at the University of Innsbruck and research director at IEEE at Innsbruck. Prof. Blatt's research focuses on trapped ions as a means to address fundamental questions in quantum optics, spectroscopy, and quantum information science. Experiments in his groups have established that ions are outstanding candidates for quantum bits in a quantum processor. Current research themes include the investigation of light-matter quantum interfaces, the scalability of ion traps for quantum information processing, and the use of trapped ions to simulate quantum processes. Next, we have Dr. Alex Kiesling, who is the CEO of QEra Computing Inc., a quantum computing startup providing access to the largest and most scalable quantum computers. Using neutral atoms, nature's perfect qubits, QEra's technology allows users to harness the power of quantum information processing systems beyond classical simulability for applications in optimization, quantum simulations, and more. Next, we have Prof. John Martinez, who is a leading researcher and amongst the founding fathers of superconducting qubits. From his work at UCSB to his position as the head of quantum hardware at Google, and the establishment of Google quantum efforts, culminating in a quantum supremacy experiment in 2019. He has worked in a variety of low-temperature device physics during his career, focusing on quantum computation since the late 1990s. He was awarded the London Prize in low-temperature physics in 2014 for his work in the field. From 2014 to 2020, he worked at Google to build useful quantum computers, culminating in the quantum supremacy experiment in 2019. He was recently awarded the John Bell Prize in 2021. Now, we also have Dr. Itamar Sivan, who is the co-founder and CEO of Quantum Machines, or QM, which is the first quantum startup in Israel. QM is the creator of quantum orchestration, a powerful integrated hardware and software platform for the control of quantum system. Designed from the ground up for quantum, the platform allows quantum research teams to realize the full potential of any quantum system. Finally, I'm your moderator, Elsie Loukiantchenko. I completed my master's at TU Delft, and I recently graduated. My thesis project was performed in QTech, where I worked with Dr. Wolfgang Tittel and Ronald Hansen on interfacing NV centers in Diamond with thulium-based quantum memory. I'm currently working at the European Space Agency in the Advanced Concepts team, and as well as I'm working with Quantum Machines, where I completed an internship this summer. I'm looking forward to being part of this enlightening and engaging discussion. All right, so our panel will be broken down into 5 parts: introducing the quantum computer, the software and hardware, the user experience, thinking ahead, and the final remarks. I encourage the audience to think of any questions as the panel unfolds, and if there's time remaining after each section, I will call for questions to be posed. So part one, introducing our quantum computers. To kick off the discussion, I will start with the main question we're here to answer. To our panelists, I pose the following questions. What is the qubit platform you expect to be the 2050 quantum computer, and why? What will the infrastructure look like? How many qubits do you envision? Will you employ quantum error correction, and if so, how? In other words, give us your idea and perspective for a full-fledged quantum computer. If somebody likes to speak up first, that'd be great.
I'll start a little bit. So I think we're in a very exciting time where people are building qubit systems, and we still have to understand the basic physics of what's going on, but there's also a lot of systems engineering aspects that we have to figure out. What happens when you scale it up? How do we make the qubits work better? And it's really hard to talk about what's going to happen in 2015 as we are still trying to understand all the system engineering issues. And so that's fine. I mean, that's where we are right now. It's interesting to think about the future. And I think as people are thinking about systems, that's going to lead into, what's going to happen in 2050. Now, just a general comment about looking ahead is I think by now, anyone who's been in this field for a few decades realize that paper qubits look the best, right? And when you build a real qubit system, you find out what all the little dirt effects are and things you have to worry about and fix. And, one has to be careful about projecting. And, clearly people who have been building qubit systems for a long time already, they know all their problems. It doesn't mean that some big breakthrough will happen, but one has to be cautious about doing that. So in terms of 2050, that's quite a few years off. And, it's kind of going to be hard to understand. I just think about what happened 20 years ago, and we were looking at single qubits and physics, and even operating single qubits was hard. But I expect in 2050, we'll be either, quite advanced, or we will have not figured out fidelity scaling issues. And we'll look back on this as an interesting time, but we don't know. We don't know that. I personally feel we still have a lot of things to fix and get working right. But I actually am optimistic. There's a lot of systems, and I think people are working on the right problems, and we'll just have to see that. I think if you look at what people are claiming by 2050, we should maybe have a big error-corrected quantum computer solving real problems. Again, there's uncertainty to that, but I think it'll be an exciting time in the next few decades.
Okay, if I may, I can continue here. John is absolutely right in his assessment, as far as I can tell. But you're asking what is the qubit platform you expect in 2050? I don't think there will be one platform. There will be quite a few, and maybe there's even platforms that we haven't thought about yet. So my guess is from the existing platforms, there are 3, 4 which are very promising, and several others are catching up. It's a race, and it's very hard to predict, especially if it concerns the future, as one of our older people have said before. So my guess is that we will see in 2050 several quantum computers, several platforms, and in the end, nobody cares of the users what kind of an engine is below the hood. They would simply use it, and there might be better technologies for one or the other subjects and problems that we have at hand. So I would not predict that there's only a single platform, unless we have a technical breakthrough that just delivers us, say, a silver bullet towards quantum computing in the next few decades. I doubt that, because you probably would have come across that already. This is going to be hard work, And as John pointed out, a lot of that concerns also system engineering. And then we come across some problems which are deep down there, and then you have to figure out how to avoid it and do it. Your question about error correction is absolutely important. There will be not a quantum computer in 2050 without quantum error correction. Otherwise, the field is going to be dead. So we need quantum error correction, and we need to solve this problem within the next, say, decade or so. Otherwise, investors are not going to believe in us and help us in solving these things. This is going to be really tough. This is my point of view, the toughest problem that lies ahead. When you're asking me how does a quantum computer look like in 2050, I wouldn't even dare to predict that. Probably it's like one of the old-fashioned computers that we have, could be a 19-inch rack, could be, say, a tabletop device. I wouldn't want to picture it, but depending on the applications, if there's a machine that can be used, it's going to be something like our typical machines of a high-performance computer that we have around there, maybe just the 19-inch racks, and that will be accessible via cloud. So that would be my best guess to that. How many qubits? I'm not sure. That depends again on the amount of error correction that how many qubits you actually need for the error correction that you're implying. And then my guess would be that by 2050, if we really have a reasonable progress, we are on the order of about 10 to the 5 qubits, maybe even 10 to the 5 logical qubits, if I'm actually optimistic about that. But that remains to be seen. It's very hard to predict this. We do have to solve these problems. We do have logical qubits at this time, but this is a single one, maybe 2. And full-blown error correction is not working yet, but it's close to. And I can see that within the next decade, these things can be solved, and then you have to scale this up. So this would be my best guess to that.
Great. Those are some really good points. And I will say you brought up a few discussion points that will be brought on further in this panel. So I'm really excited to hear about other people's opinions on that too.
So I want to build a little bit on what Rainer is saying. And I think that really thinking about the end user is key here. We have a lot of different qubit platforms, but at the end of the day, the only thing that matters is that we create something that is useful. And to me, one of the things that is hardest to predict about 2050 is that right now we have an idea of how we use computers. And we've identified some problems for which we use computers that we expect quantum computers will help us with. But I think that from now till 2050, there is a lot of room for exploration and for discovery. And that may end up being that the kinds of problems that we're thinking about are not even the most relevant for how we will be using the machines in 2050. And at the end of the day, the technology that we develop has to be tied to the way that we want to use it, the way that we want to use it. In some ways, this is something that we're seeing nowadays with specialized hardware that is built for specific purposes. And I think that we'll see something similar with quantum computers. Right now, we see it already because we have different architectures and different platforms that play to their strengths and try to avoid their own weaknesses. I think that in the future, we will see using different types of platforms and integrating them in a way that really leverages all of their strengths and minimizes the weaknesses that they have. So the way that we have built computers in the past that use magnetic memories or where we transfer information using light, I think there's a lot of room here to really bring together the different qubit architectures and to also stay open to be surprised to what we learn from now till 2050. And yes, I think that quantum error correction is key. I mean, there's a lot of work already being done in this direction. I think that we'll also learn a lot about how to think more holistically about how to reduce the errors, not just, I mean, yes, correct for them, but we also need to do a lot of error mitigation and to design our algorithms around the kinds of platforms and architectures that we have nowadays. And this is really what's going to get us that extra information that we need to design the 2050 quantum computers.
If I can just add to that, so I agree with the several statements that were made about, well, basically the necessity of having error correction and also the likeliness of having multiple types of qubits in the same computer. And I think that maybe another reasonable assumption is that just as essential to have quantum error correction, it will also be essential to separate the quantum processing unit, like the processing area, from actual storage, right? From the actual memory. Just like it happened with, of course, with classical computation. If you really wanted the computer to be scalable in many regards, quantity of the number of parallelized operations that are done in a quantum processor will also be limited at some point, limited by us from an architecture perspective. And I think that ultimately having separated the QPU, where the processing qubits from the storage qubits is going to be essential, and also one of the biggest challenges, because of course, if you separate them, so it means that you do not process all qubits simultaneously, but still you need to keep coherence or entanglement throughout the entire system. So throughout the qubits, which are maybe now stored, the data that is now stored, they still need to be to keep their coherence and entanglement to the rest. And I believe that also another aspect which is crucial is the diverse of customized classical control and co-processors. I believe maybe we'll have time to elaborate about that later on. But so I believe that there will be, of course, diversity of quantum platforms, but also a diversity of classical processors which are dedicated for the controls. Again, just to support the scalability of the system. And in addition to that, so assuming that at some point we'll reach the quantum error, we will reach quantum error correction, I think that much of also the speak and the metrics that we're using will also change dramatically over time. So from kind of the year-over-year qubit count growth, what we're kind of measuring now, just qubit count and maybe even quantum volume, will completely change at some point, likely to discussions about speed of the computers and the dollars they cost us, and other metrics which are much more typical for a real industry, just as it is with classical processors. I mean, we look at the gate size, right? The gate size is related to things like speed eventually, or the clock speed, right? We don't look at the number of transistors we can fabricate. So in a similar way, the span of metrics that we're going to use are also going to completely change.
Yeah, those are all really good points, and I'm personally interested to see, this is a question that I'll have later about the benchmarks that we use to classify whether the quantum computer is good enough, could become, maybe simulating some chemical compound that we haven't been able to, or having some sort of useful problem that we're trying to solve. And yeah, those are all good points. And all of these are actually really good lead ups to the first part, which is the software and hardware. And my first question is a bit more high level, which is, at what stage will this quantum computer be? I hope that we're not going to be in the NISQ era anymore, but will this quantum computer actually be fully mature by 2050, or is that a bit too optimistic? And what kind of algorithms will we be able to run, and what solutions will we be able to provide? And I guess the biggest question is, in 2050, do we expect quantum computers to be able to shape our society, our economy, or technology in general, or is that a bit too far-fetched for 2050?
Excuse me, Elsie, I would have liked to hear Scott Aaronson's view on the hardware first before you go into the software stuff. Can we have that?
I'm so sorry. Yes, you're completely right.
So, I mean, I feel incredibly lucky as a theorist, sort of not to have to place a bet on which hardware is going to be the right one, right? I can talk to everyone, and I mean, I feel like it could be superconducting qubits, it could be trapped ions, it could be photonics, it could be a combination of them, it could be something that hasn't been invented yet, right? And all of the approaches that I've mentioned, I mean, the partisans of them can convince me while I'm talking to them that they have the only way to scale, right? That nothing else can work. The problem is simply that the next day I'll talk to the partisan of a different approach, and then I won't be able to recapture that state. But I think what we all sort of hope for the most is some platform that would have fault tolerance kind of naturally built in at the hardware level, so that it wouldn't need to be laboriously put in, at the software level, via a fault tolerance and via error correcting codes. Now it's possible that topological qubits could be a step toward that, but there is not been a lot of success so far at creating even one topological qubit, right? So and even if that does succeed, it would not entirely eliminate the need for error correction. So I think that we should think of ourselves as in the quantum computing analog of, let's say, the very, very early vacuum tube era, or electromechanical relay era, right? If there is a quantum computing analog of the transistor, I don't think it's been invented yet. Okay, so what will the infrastructure look like? Maybe I can say a bit more about that. I mean, I think that for the foreseeable future, the thing that I envision is quantum computing being available to those who can actually use it as some sort of cloud service, right? I constantly get asked, like, when are we going to have personal quantum computers, or a quantum computer in our iPhone or whatever, right? And I'm reticent to say that will never happen, because of course the people who said the analogous things about classical computing in the 40s and 50s are now ridiculed for making some of the most wildly wrong predictions of all time, right? But having said that, if you look at the people who said that no one's going to need a classical computer in their home, things like that, they were actually just thinking further ahead. Ironically, they were thinking ahead to what we would now call the cloud, to thinking, why do you need all of this computational power in your home if you can just get it, tap into it on a network? And ultimately that is right, and that is the world that we're heading toward. And I think certainly with quantum computing, it's very hard for me to think of why someone needs a personal quantum computer when, for the special applications where a quantum computer helps, and as far as anyone knows today, they are rather special applications. A quantum computer is not going to help you much for checking email or for playing Angry Birds, or it will help for with physical simulation problems, maybe eventually with some optimization and machine learning problems, the people who need that, will be able to get it with, the quantum analog of Amazon AWS, things like that. How many qubits do you envision? I mean, if it's actually going to be useful, then I would say probably millions. At the very least, millions of physical qubits. Ultimately, if you're going to be seeing advantages for, machine learning, optimization, stuff like that, probably even millions of logical qubits. As I said, I don't think that anyone has an idea for how to scale quantum computing right now that would not employ at least some amount of quantum error correction. Okay, but the better the underlying hardware, the less error correction you would hopefully need.
But maybe if you'd like, you could, I know you just spoke, but perhaps you could be the first one. I'd like to hear what you think these impacts. would be.
All right. Well, I have no idea whether we're going to have, let's say, a fully error-corrected, fault-tolerant, scalable quantum computers by 2050. I think that it is reasonable to hope that we might. I mean, if you look at, let's say 30 years ago, well, that was 1991. Even the most basic quantum algorithms had not been discovered yet. There was no theory of quantum error correction. Now if you look 20 years ago, much of the theory was already in place by then, but the experiments were not. Right? People were, as John said, they were trying to get individual qubits to work, or individual 2-qubit gates to work, right? And all of the progress in scaling that we've seen over the last 20 years has been really impressive to me. It's been there have been just orders of magnitude improvements in the fidelities of gates, and if you just look at a plot, of here's how the fidelity has been changing over time, and here is the fidelity that you would need for fault tolerance to work, then that can make you feel very optimistic, right? That, maybe it's just another decade or so, and then, we're well past the fault tolerance threshold. I mean, extrapolations like that are always very difficult though, right? And, the fear is that, it becomes like fusion energy, right? Where it's, there's always another difficulty that pushes it further into the future. Although I hear exciting things about fusion energy right now. So, maybe we'll have that as well, right? What kind of algorithms will you be able to run? Well, I mean, once you have a fully universal quantum computer, the whole point of universality is that you can then run any quantum algorithm, right? Now, unfortunately, we're in this situation where the scope of quantum algorithms, I think, has often been massively oversold, right, to the general public, to the business community. People have gotten the impression that quantum computers will just give exponential speed ups for anything by just trying all of the possible answers at once, and it's not that, right? That's not really how it works. The basic picture, that's been in place for, a quarter of a century now has been that quantum computers can give for a very, very wide range of problems. They can hopefully eventually give us polynomial speed ups, like the square root of the number of steps that you need classically using Grover's algorithm or its variants. But in order to actually see a benefit from Grover's algorithm over what you could have done classically, the most recent calculations say that you're going to need an absolutely massive device, like possibly billions, trillions of qubits, right? And very, very fast gate times, right? Because it's only a square root speed up, it's very, very demanding if you want to actually not only do something, but crucially outperform what you could have done with a classical computer. So it's possible that even after we get programmable quantum computers, it will still be quite a while after that before we see advantages from Grover type algorithms for things like optimization or for machine learning. Now, what we're likely to see much sooner is advantages for problems that themselves involve quantum mechanics. Okay, simulation of condensed matter systems, maybe even simulations of chemistry, learning about the ground states of interesting physical systems. And then, of course, there's breaking public key cryptography, which will be, maybe people will take that as sort of their sign that, scalable quantum computing has truly arrived when that becomes possible. And that will probably happen, not long after you get fully scalable, error-corrected quantum computers, although not before that, right? You really are going to need error correction for that. And, and then beyond that, there's a whole bunch of possible, near-term quantum algorithms that get talked about a lot. Things like this QAOA or quantum annealing, various quantum machine learning algorithms that I think of as having more of the character of Hail Mary passes, right? These are things where, we even heuristically, we don't really know, we can't really articulate why are they going to give you a speed up over the best you could do with a classical computer, but we can't prove that they don't give you a speed up, right? We can't rule out the possibility that they do. So these are things that are worth trying, where people are going to explore them, learn more about them, even before we get to full error correction, even in the era of noisy, intermediate scale quantum computers. We're going to be experimenting with these algorithms, and maybe some of them will give some, practically important speed ups, but we can't really bet on that, given what we know at present.
I think that last point is key, though. I think that it's hard to predict what's going to happen in terms of algorithm development from now until 2050. But at the same time, when we use computers nowadays, yes, we are aware of limitations and how hard it is to solve certain problems generically. But at the end of the day, we go ahead and we type something on our computers and we get reasonable results. And we have heuristic algorithms that get us pretty close to good enough solutions, even if they won't necessarily work in the worst case, and the scaling is hard.
To be clear, I wasn't talking about worst case. I was talking about even just getting an advantage heuristically. Right,
but I think I don't disagree with this, but I do think that we are entering a very interesting situation where we have devices that are getting to be large enough to put in people's hands and let them explore. And I think that there was a big revolution in computing by giving access to everyone to computers. And that really led, just by trial and error, that led to huge advances. And I think that this is going to be true with quantum computing as well. And I mean, right now, during my PhD even, we got to work with systems with 256 atoms. And we started learning something about, very specialized topics and condensed matter and so on. But I think this was also coming from the fact that this is the kind of language and the kinds of problems that we think about on a daily basis. But there are other people out there who are thinking about different problems and who will have a chance to develop the new algorithms that will be useful to them. So when we talk about what are quantum computers going to be used for, I can give answers, and I guess Scott, you just did. You talked about some of the possibilities, even just cracking codes and so on. But I think that the next 30 years from now till 2050 are going to be very interesting in seeing what do people really want to use these machines once they're in their hands. And if we had tried to make a prediction 30 years ago about playing video games or even just things like Zoom, right? I think it would have been hard to make accurate predictions. I think some would have said it was laughable. So I think there's a lot of place to adapt the technology that we're developing for the applications that people are running. And therefore, what solutions will you be able to provide? I don't know. I think that this is on us to really build a technology that is enabling the applications that people are looking for.
People were definitely talking about video conferencing in 1991.
By the way,
the Jetsons, I remember this being
there's a very famous marketing book. I'm not sure if physicists among you actually read it. It's called Crossing the Chasm. It was published in the 90s, and it discusses two things, two technological things that didn't ever find any good problem that they solve. One is video conferencing and the other is machine learning. So kind of talking about ideas that never found a real world application. At least one of them we're actually using now. So, but of course,
well,
this is
you know, for both of them, having the idea was one thing, and you needed enough computer power before it actually became practical.
Yeah,
both of them actually. But
I think that at least here we know a possible endpoint, right? Like we know there are applications that we care about, and it's worth building these things, even if just for those applications.
Oh, absolutely.
But there will be many more to come.
Yeah, no, I mean, I think the tricky thing about quantum computing is, you know, absolutely there will be more quantum algorithms, you know, to be discovered. I hope that, you know, my students or, you know, my group will be, you know, we'll discover some of them. You know, I mean, this is what we do. But there will also be more new classical algorithms to be discovered, right? And the hardest thing about, you know, being a quantum algorithms researcher is that it's not enough to succeed. You have to do better than anyone could have done using a classical computer, right? And it's that comparative question that really, you know, makes things so difficult in this field.
And also many times your quantum algorithms inspires the classical algorithms that get better.
Yes, that as well.
Well, that's great, but okay, we have a steep hill to climb.
Yeah, absolutely.
Can I add just another 5 cents here? You're talking all about, say, either big data or some algorithms computing things here. But the majority of computers is not big mainframes. It's mostly microprocessors and small scaled down processors that are doing measurements. What I really foresee is there will be a whole industry of improved measurements using all the quantum technology that we are developing right now, very small algorithms that can be used in little machines to improve here and there. And I think this is much more valuable on the way towards the realization of the big machines. Eventually they will come, but I think there's a big industry before us, and there's a big number of applications, really small measurement algorithms, optimizations, and things like this that are not visible yet. And we have to supply the users with toolkits and with the capability to make tests. And that will be, I think, the majority of things that we do for the next 20, 30 years until we have mainframes.
Yeah, those are all really good. Thank you for your in-depth answers to all of these questions. And I have to say, I think the biggest takeaway is that I think when you look at the way people looked at classical computing is, yeah, nobody would have really thought what we could do with it. So I like the idea of giving something to the people and saying what they come up with and what they create, and they will find the problems they want to solve. And I think that's a very good point. We kind of touched on this a little, but maybe it's interesting to talk about whether or not we think, you know, do you see one qubit winning out at the end, or is there room for a lot in the future of quantum computing? There are also various architectures for how these quantum computers are organized. Will they converge, or is it okay for us to just have a lot of different things to go, you know, directions to go? And I guess similarly to what Itamar said, there could also be different architectures or different platforms for quantum memory versus the actual computing that needs to happen.
As Scott mentioned earlier, every experimentalist thinks that his platform is the best. And I certainly feel that way about superconductivity. It's natural, and that's fine. Okay, and like I say, what's great now is everyone gets the chance to do that. And it's going to come down to solving some basic physics problems that have been overlooked, and also doing all the engineering about what system will be better in the long term. And we just have to wait. I think in the next 10 years, for example, maybe it won't take 30, but in the next 10 years, we'll begin to see which systems are more favorable and not. People are making a lot of bold claims right now. Let's just see if it comes true and what all their problems are. And yeah, probably in 10 years, we'll know a lot more about what's possible and what's not. And then, of course, there's always room for surprises, which is what's great about physics. And we just have to wait and see on that.
I think the same way. In the end user doesn't care what engine is under the hood. The main point is you have to solve a problem with it. And then, of course, there will be a competition. If some company or some better quantum computer is around to solve the problems easier, that may be a winner, if after all. My guess is there will be several engines available, and then we'll have to see. And there may be the breakthrough technology that still has to be found. It would very well be that the new kid around the block finds a technology that works much faster and much better than anything else. So be it.
That would be quite exciting, wouldn't it?
So if I can just add to that, so I think, like, in my opinion, on if we look at 30 years ahead, then of course it is possible to believe that there will be multiple qubit platforms that are kind of at the same level, but then still it is very likely to believe that some of them will be much better for some things, and the others will be better for other things, right? So there are two questions here, in my opinion. Like, one of them, are we going to have quantum computers based on different qubits? And the other is, are we going to have quantum computers with multiple types of qubits? Which, in my opinion, is much more likely to believe, because, I mean, the platforms that we're playing with today are fundamentally different. I mean, ions and superconducting qubits are so different, so that on the scale of 30 years, it is likely to believe that they will diverge into being optimized to different roles.
I think, Itamar, you said this earlier, that it's reasonable to believe that there is going to be a processor that is going to be separate from memory, that is going to be, potentially separate from like QRAM versus long-term memory, right? I like to think about the progress that we're seeing as developing modules that then will build larger systems. But whether it's, in one computer, you only have one type of platform, one type of physical qubit, versus you have integrated different types of qubits within a single machine. To me, the thing that seems more important to start tackling is, let's say we get there, right? We're going to need standardization. We can get to the point where we're using different physical qubits, even different architectures, but to be able to really leverage the power that we're getting by building all of these things, we need for information to be able to be transferred from one module to another and from one machine to another. So I think that standardization in the way that we encode information, that we transmit it, and that we even exchange it from one physical platform to another is going to be key. And if we cannot do that, then I think we're going to be pushed to having to choose a particular physical qubit. But that is not, I think, the best potential outcome, because we really should be leveraging the advantages that we have in the different physical qubits.
I wanted to just make a quick comment here. I agree transferring information and communication is very important, and transferring one qubit type to another is nice. Somehow everyone gets the idea by combining qubits, different qubit types, you get the best of both worlds. What I've seen in some specific examples, it may not be generic, is you tend to get the worst of both worlds, and that combining different qubit technologies is a lot harder than you think. So this is great, people should research it, but we have to be very careful that that's a magic bullet. And I think part of the problem here is we have so little margin, say on gate errors on qubits, to do that effectively, as an example. But again, this is all up to future research, kind of systems level research.
I mean, we have seen examples of experiments that used multiple types of qubits to good effect. Like the first loophole-free Bell test, right? Used photonics to sort of get the distance, and then to get the measurement accuracy, the entanglement was transferred from photons into envy centers and diamonds, right? So you needed a hybrid of both systems, right? But we've seen many other experiments where you only use that experiment was later done using only photonics, I believe, right? So one could imagine a hybrid, or one could also imagine the analog of what happened with the transistor, right? Which is that a building block for classical computing was invented that was just so much better than everything else that it eventually people just gave up on combining or hybridizing, and they just went with that one.
Yeah, and just be aware there's a difference between a physics experiment and doing really careful systems engineering. And again, we're going to figure this out in the next decade or two.
Those are all fair points, and just for timing, I will move on a little bit. My next question is about quantum control and what kind of if we have a certain number of qubits, which we hope to be a lot, we will need to have some sort of quantum control that handles all of that. And what are the challenges we'll be foreseeing in 2050? And are there ideas about how to mitigate that?
There's the usual problem, what you're talking about. You really want to go with the quantum technology to a macroscopic world. So you have to really control a macroscopically quantum system, or a macroscopic quantum system. And this is the challenge that we have been facing now for decades. And this is even worse if you go to such a large scale. And so the challenges are the same, and the error correction, as I said before, is absolutely vital in order to get there. But then, of course, it's the technology that makes progress. We have seen in the technology a lot of progress, better materials, better light control, better interfaces, and things like that. This goes hand in hand. But in the end, you can beat, you can never beat physics with technology. Technology advances physics to a certain point, but in the end, you have to come up with better ideas in physics to beat the technological limits that are imposed by what we have. And I think this is work that goes from the science labs into as John says, to the systems engineering, which is daunting, but this is what's necessary. We have to jump through a lot of hoops in order to get there. And I'm sure in the end we will get there, because I don't see a physical roadblock. There's no law of physics that doesn't allow me to control such a macroscopic system. This is the challenge.
I very much liked talking about a macroscopic system, because let's say 20 years ago, 30 years ago, we're trying to control a single qubit. And by making the qubit big, it was kind of easier to get the control signals in there and do that. And that was a key component. And then what I would say is, as we do work to control these very complex systems, we have to remember that our control systems are typically a little bit complicated. It's an analog system in the end you have to control. And you just think about it, you have some waveform generator, there's a kilobyte, 10 kilobyte of information to control that in the various ways you want to do. And what I'd like to point out is that just the physical memory of that means there's size to the control system, just in the memory, but of course in the D to A converters and the transducers and everything else you're talking about. And because there's a physical size to this, it again points to this macroscopic system that's kind of big enough to match whatever control system you're building. Now, right now, the control systems are about this big, right, for a single channel, okay? And when you think about the memory and the chips and the like, that can undoubtedly be shrunk, and then you can figure out how to do the wiring. But I think there's a fundamental challenge in matching the size of the control systems with your size of the qubits. And I think people are going to, figure out various ways to do that and come up with various things. I think in some sense, that's almost the most fundamental question on how to do that right with control.
I most definitely agree. among other reasons, because at quantum machines, this is basically what we do. We work on quantum control and orchestration, and I think that indeed, as John said, this is a fundamental thing. You can think of it even in terms of the number of controlling bits, the ratio between the number of controlling bits to the number of controlled qubits. Right, today in most groups, even leading companies, you have an FPGA controlling a dozen qubits. Right now, if you multiply both by 1,000,000, of course the control explodes. Right, and this is a fundamental thing which stems from the fact that we're controlling quantum systems with classical systems, right? And the difference in basically the space that they live in, and I think that in this regard, so there are a few interesting directions that we can go about this. By the way, one is related to what we said earlier. So if we separate the processing qubits from the memory qubits, then of course, each of them needs a completely different set of controls, right? Or not completely, but there's some overlap, but there are also some elements which are not needed in both. Then, of course, so the separation goes into the second hierarchy when you separate the control of the qubits from basically the physical qubits all the way to the single logical qubit, and the controls going from the physical qubit, from the logical qubit to the QPU, right? Again, in terms of control, these require different knobs. And if we want to basically, if we want it to be scalable and not eventually in terms of space, right, as John said, then these have to be separated in the control stack into different units, which by 2050 will likely be different ASICs, right? So we will have different processors which are responsible for different operations in the quantum computer, from the processing to the error correction, sequencing, shuttling data back and forth from the memory to the processing unit, and so on and so forth. And even just for the trapping and cooling, which of course Alex and I are working on as part of the computer.
Okay, so just I don't want to cut off the discussion, but I mean we can talk about this for probably 3 hours at least. But we only have 90 minutes. So I'm going to move on to the third part, which is the user experience. And my first question is about, what kind of level of abstraction will we be expecting in 2050 in terms of even the programming language that will be available? What kind of knowledge or level of knowledge will the end user require to be able to operate these quantum computers? And yeah, what will the actual user experience look like? I think that's an important question to think about, especially if we're thinking about the people who are going to be creating the problems to solve them.
I'm just going to say, I think what was really powerful for our field is this circuit language was invented, in the 1990s or maybe before, to describe the gates and what you had to do. And that kind of universal language has helped experimentalists know what to focus on and kind of conceptualize what's going on. So I think that's one of the reasons the field has done so well, is we've known, what are the elementary gates, and you have to do that. And I think if you look at all the different varieties of the programming language right now, let's say, ignoring D-Wave, which is a very different machine, or maybe some simulator machines, but most of the circuit machines, they have a common language, and we can go between the two. Now in 2050, I imagine this will be abstracted some more, and I think that'll be interesting and good. But I think we're in good shape because we have this common language. It's kind of like Boolean logic. If you have an AND gate, you have a NOT gate, you can then build anything up from that. And given that very foundational description of the field, then it's easy to break the problem up between hardware and software and conceptualize it properly.
At the low level, I agree with you, John, but I think that, at the high level, there's there's no reason to expect that people will be, programming things with C naughts and so on in the same way that nowadays we mostly don't use ands and nands and so on. And I think that by 2050, we will have built kind of more standard libraries, even if they are for small problems. But we'll have standard libraries that people will be able to call, right? You don't need to know exactly the details of what's going on at the hardware level with your machine to be able to write something in Python today. And I think that will be true with quantum computers in 2050. Even more than that, I think that the way that we're going to be using them might be integrated into some other applications that people are using nowadays. And for the problems where we identify they are useful, it will be as easy as choosing from the different options that you have in whatever software you're using for chemistry or whatever, to just pick to send the abstract code that you've written to a server, for example, that is a quantum computer. And then it will translate it into the correct formulation for the quantum computer to run the quantum algorithm. I think that at the end of the day, this is not going to be successful unless we make it user-friendly.
I mean, I think it's safe to predict if quantum computing is going to be used to, post videos to TikTok or to play video games or things like that, then, it will have to be, used in a way where you don't need to know anything about quantum mechanics in order to do it, right? But as I said, it's not obvious to me that quantum computing will be used for any of those applications, because it's possible that classical computing will just be perfectly adequate for much of what the end user wants to do, right? And where quantum computing will really find a huge economic niche will be things like designing new materials, designing new chemical reactions. And there, the sort of the bar is lower because you just have to make it accessible to the same kind of scientists who would now be using a quantum chemistry package, or a package for simulating material science, right? And, they too might not want to know all of the details of the quantum computer, but, they know something about quantum mechanics, and if you can provide them with a tool that they can use, then that could be, really powerful.
And of course, right now, what's nice is there are quantum chemistry tools and machine language tools already, and they will evolve. So I think the field is doing a good job here.
Yeah, but if we want to think about, let's say, banking and all of that, I guess that's maybe further than 2050. Somebody who's a data analyst might not necessarily want to, speak the quantum language in order to be able to actually use it and perform some optimizations that they require, right? I think it's interesting what Alex said.
Yeah, your existing classical computer does all kinds of things to accelerate, it has a graphics card to accelerate the graphics, right? It uses all kinds of interesting algorithms, right? At the hardware level, it uses pipelining, right? How much does the ordinary computer user have to know about any of that, right? Basically nothing.
And you see it even with something as simple as a fitting routine, right? You write in Python fit, and then you just get something. At the end of the day, there's a lot more that goes into that, but you as the end user don't need to have extensive knowledge about it to make it work.
This is an interesting question that I heard in a lecture I listened to recently. Some believe that by around 2050, the quantum computing problem will be physics de-risked. In other words, it will turn away from a physics problem into an engineering problem. And some people would even say that it already is like that. What do you guys think about that? Is that transition going to happen? And if so, when? Or I guess in a more scary way to put it, are we out of a job in 30 years, the next people working on quantum computing?
I don't think
I'm lucky that I'm not a physicist. I'm a computer scientist. So, eventually computers might design algorithms too, and they might replace us for everything.
Yeah.
Will have, I have a lot of friends in the Bay Area who worry about such things, right? But, I feel like, designing. I mean, look, it's been we've had generations of classical computing, and yet people still design new classical algorithms that are needed to do that. I think quantum algorithm design is something that has a lot of juice left in it.
I think if you look at CMOS transistors and Moore's law scaling in the last, I don't know, 40, 50 years, have they stopped thinking about physics and solid state physics as they've designed these? No, you still need people to understand that. I would say maybe the fraction of physicists have gone down,
Exactly.
but the total number of physicists has gone up because, of course, the field gets very big. So that's kind of the way I would imagine it working. And there's always going to be some new physics for us to understand to make the machines look better.
So yeah, so if I may, so yeah, the percentage of physicists is immense because the quantum processors are not properly working yet. But if you see, yes, so if we want to advance the transistor, then of course physicists are working on that. But the majority of people who are developing classical processors today are not physicists, right? I mean, even the companies that develop processors, I mean, they don't even fabricate processors today. I mean, NVIDIA, Qualcomm, and so on and so forth. These companies, they just go to TSMC and they do it there, right? And even at TSMC, they don't do the physics. It's being done at ASML and applied materials. So I think indeed the percentage would go down substantially, and also where they are. So the physicists will not necessarily be occupied with looking at the entire processor, but just focused on the qubit. I don't know if it's 2050 or after that, but at some point.
I don't see a risk for physicists running out of business here. I think physicists will have a new tool with which they develop new fields and they will understand fundamentally new things. I can think about, say, quantum correlations across large distances, which open completely new fields for all kinds of physicists. I'm sure there will be plenty of questions. The more we see with the new machines, the more we learn and the more we know what we don't know.
I think there'll be a lot of physicists as consultants who will have to cut through all the marketing hype that's coming. Putting out there.
Indeed.
Oh yeah, absolutely.
I'm glad you appreciated that. That's how I feel.
I feel like so many people look at it as an panacea of quantum computing just will solve world hunger and climate change.
I have advised companies, that you should hire a quantum computing expert defensively to sort of protect you from, quantum computing hypesters who are going to try to mislead you, right? And that could be one of the big employment opportunities for our quantum computing graduates for quite a while.
That's good to know. Good to know. Sometimes I'm worried, but I should have got into this field like 20 years ago, and that right now we kind of are in a different place with that.
Would have been impressive if you got into this 20 years ago.
Well, I would have had to be born a bit earlier, I assume. And I guess in a similar idea, my next question is the fact that right now, maybe this is a bit of a provocative question or statement. I would say that the world of quantum computing is still largely ruled by academics. But do we think that in 2050, industry will play a larger role or maybe even a smaller role in the quantum ecosystem? And we have, some people in industry on this panel, some in academia. I'd be interested to hear your opinions on it.
I think the answer is definitely. I mean, 20 years ago, what was the industry, right? Even now we see more of a role that industry is playing. And it's because of all the work that has been developed in academia. I think that as we collectively as a community continue to be more and more successful, there will be more an industry presence. I don't see how industry will not have a larger role just because of the fact that it is growing nowadays.
What if we get some sort of quantum winter, like the AI winter, and then all of a sudden we have to go back to the drawing boards and think about another situation altogether, and then it all goes back to academia again. And then I will get my turn to shine and come up with something.
We've already gone through quantum winters. Let's say maybe 10 years ago, I remember talking to people that they were wondering what was going to happen. There might be more, but I think we've shown enough now to justify serious investment, and that's what people are going to do for 5 or 10 years, and we'll see what happens. And there will not be a quantum winter if we can get our promises to work. It's up to us. That's what's nice now, is we have the money to do our ideas, and we just have to get it to work.
I wanted to say, I'm not even sure that the presupposition of this question is true right now. You know, I mean, it was true 10 years ago, right? I mean, I think that, as late as 2010, quantum computing was largely an academic field.
Right.
But today, 2021, I mean, we have seen investments from Google, from IBM, from Microsoft, from Amazon, from this whole bevy of startup companies, that are at a level that academia can no longer match, right? And this is the new reality, right? And, like my students, when they get their PhDs, like where maybe a decade ago, it would have been obvious that they would go into academia. It is not obvious now, right? And now some fraction of them are, indeed, going to go into industry, or they're going to be snapped up by IBM or by Google or whoever else. And so, so I think that to a great extent, this change has already happened, and it's natural to expect that if and when this really becomes a sort of self-sustaining commercial enterprise, right, then it will happen more, right? If the commercial enterprise fails, then maybe it reverts to being an academic subject.
Yeah, and I made that switch 7 years ago, and in part because it was going to be hard. I could see it was going to be hard to succeed in academia because of various subtle funding issues. And I think for experimentalists, there's definitely advantage there, but still there's academic groups can do a lot. It's good that there's an ecosystem and people are working on different things. I think this is healthy. And I think it's great that students, for example, have more employment options, because some are more academic oriented and some are not. So I think it's a very healthy change in the field.
It's hard to predict whether this is going to exist in 2050. That depends, as John said, on our success over the next years. But with all the startup companies we have seen over the last, say, 2 years, the foundation of about 150 startups by my last counting. And this is pretty amazing what's going on there. Not all of them are going to survive, but some of them will become very big, as we have seen already with some companies. And so the ecosystem is definitely stronger in the quantum world than it was before.
I think it's interesting to see this question right after the previous one, right? Because in some ways, if we assume that there are going to be more engineers, it also tells us that it's because the role of industry has grown. And the reason why it has started, one of the reasons why we see more industry involvement is precisely because in an academic setting with people who are there only for a finite amount of time, who have very specialized skills, it's hard to build a large enough, strong enough team with the right background to fulfill all the different things that you need to make a useful product out of a quantum computer. So I think the fact that we have more engineers nowadays starting to enter this quantum ecosystem is an indication that industry is starting to play a bigger and bigger role.
Yeah, that's true. I guess we'll see what happens. I hope it continues to play a bigger role, and I hope that we get to see it progress in that direction. Time will tell more than anything. And this is the last question I have prepared, but if we have time, I'll open this up for questions from the audience. But what do you think will be the next challenges for the 2050 quantum computer? Where should we put our efforts even now to prepare for it if possible? And I think that's a valid question. If, let's say we get great gate fidelities and let's say quantum error correction, we see it's possible. What are the next big blocks for us to move through as the community?
Are you talking about quantum information processing, or are you talking in more general terms?
Whatever we want to go with it, I guess. I was looking more into, yeah, perhaps the process. Yeah, you answer that however you want. How's that?
I mean, you know, we've seen in the past couple of years, you know, the first really serious claims to get quantum supremacy, right? Or, you know, a clear speed up over a classical computer from a fully programmable quantum computer, right? First from Google, you know, now from USTC. And, you know, the way that I'm thinking about, you know, the next 5, you know, let me speak just about the next 5 years, because, you know, I feel like that there's enough uncertainty there without having to worry about the next 30 years, right? But, you know, the way that I think about the coming years, you know, we need to sort of achieve quantum supremacy with, you know, near-term devices, which are not going to have full fault tolerance, right? But, you know, we need to do it in a way that will withstand, you know, the efforts of classical skeptics to, you know, nullify the results, to sort of spoof them with a classical computer. Ideally, you know, we need to do it in a way where a classical computer can easily verify the answers. Right now, even just verifying the results of these experiments requires, you know, a massive supercomputer, right? And then that's something that doesn't scale. So, and ideally, we would like to, you know, achieve quantum supremacy, you know, not just for a completely artificial benchmark, but for some task that is independently interesting or conceivably even useful to someone, right? And so, you know, so I see these as very big goals, you know, to aim for, you know, within the next 5 years, you know, that are not, you know, like, you know, so far in the distance that, you know, we can't, you know, be productively thinking about them right now. You know, and you know, the longer term goal is to get, you know, qubits that are error corrected, right? And you know, we're just now beginning to see, you know, sort of logical qubits that sort of stay alive for maybe, you know, a little bit longer than the underlying physical qubits are staying alive for, right? But to get from there to a full, you know, scalable, fault tolerant system, you know, that's going to be a long journey, right? And the, you know, the question for the next 5 years, let's say, will be what kind of interesting, you know, verifiable, useful quantum advantages can we get, you know, even before having full fault tolerance.
In my point of view, the biggest challenge on the fundamental side is the control of entanglement over large scales, meaning time scales and spatial scales. And you have to be able to verify, as just Scott said, our results. How do we know if we had, say, for example, available, say, 1,000 qubits or 10,000 qubits and do computations, that these computations are really true, that the results are exactly true? Of course, there's ways to do that. Now you can have, say, 2 or 3 quantum computers that can be compared and things like this. But in any case, verification, validation of the results is very important. And also, how do you know if you're sitting, say, on your desktop and you are remotely connected to a quantum computer, that this machine is actually quantum? Can you control this? Do you know how to do this? I wouldn't. And there's a number of things that I see on the fundamental side. And then, of course, the fundamental technologies that go along with these quantum correlations that we now can control on a large scale, that go way beyond anything like quantum information processing. I think this is deep fundamental physics that I would like to see. And we can go to precision measurements, we can go to scales, we can see other phenomena that we couldn't see before, non-local phenomena, things like that. I can see a myriad of physics things that I want to concentrate on as a scientific community. Maybe that's not so much of interest to industry or to applications, but for a fundamental point of view, I see tons of questions coming up here.
Yeah, so just to kind of address what I believe was your question, Elsie. So you're asking of what will be the new challenges when we get to 2050, right? So not even one of the challenges on the way there. So if what was said here is true, and we're going to get by then to fault tolerance and to a great number of qubits, then of course, well, not of course, I believe that the next challenges would be actually QPU to QPU communication. So quantum communication across QPUs, because true scalability goes beyond a single processor. Just like in classical computing, of course, there is some limit to what you would want to do in terms of architecture in a single processor. Then we go to multi-core processors. And then if you look at a data center, a high performance computing infrastructure, of course, it's all about the entire infrastructure. So I think that if we indeed sort this out, error correction in decent scale, then the next challenge would be to orchestrate algorithms across QPUs and sorting out the entire architecture.
From the hardware point of view, I want to focus on two things. And my feeling is if we don't do these two things right, which are pretty simple, then this is just not going to work. And you're limited by it now, and we just need to solve the problems. And you have to focus on the big issues in order to fix them. And the two issues are, we need to have lower gate errors in a scalable system. And scalable system might only be 5 qubits or 10 or 20 or 50, just big enough to know that you're doing something reasonable. Now, where are we right now? Well, most systems are about 1%, 0.5%, maybe a little bit better. Okay, so you can do a quantum supremacy experiment, but it's not good enough for doing error correction, which would lead at least 0.1% and probably 0.01%. 0.5% is not good enough for any NISQ applications. Maybe if you're at 3 times 10 to the minus 4 to 1 times 10 to the minus 4 errors, you could do something, okay? And this has to be tested very carefully. Now, what I find is very strange is as I read papers about some new result, people are not quoting their just simple gate errors very well. They may quote it, but there's no description in the supplement. You don't know what they're doing. You don't know if the gate errors gets worse over time because various errors build up over time. And if people don't seriously address this, then how are we going to improve the metrics? Now, one thing I would say that I loved about the effort in China is that they're doing the quantum supremacy kind of experiments where you get to test these numbers. And that's why we did the experiment at Google, is we could see how things are working, see if things screwed up when you were made a big system and all the like. But I don't see, especially in the West, this being taken very seriously. And for example, I was looking at a pitch deck this morning, some company explaining they're going to make 10 to the minus 6 2-qubit gates, which I suppose is possible, but 2-qubit gates have been stuck around 0.5% to percent for maybe 10 years now. Okay, come on, let's get realistic. This is hard. We have to work on the fundamentals. And if we don't do that, our quantum computers aren't going to be very good. Okay, now just going beyond that, my second statement here, which is related to this, is we're now starting to make logical qubits. Okay, and the logical qubits are a little bit better than the physical qubits. But because the error rates are not very good, that's not great. Now, what we should be talking about is your experiment going to enable you to make a 10 to the minus 15 error rate logical qubit? Okay, because that's what we want to do. And what do you have to do to build that? That's the end goal. And right now, just using the rocket analogy, we're making bottle rockets. It's launching off the ground. We have a little bit of error correction, but we need to get to the moon and build a Saturn V. And there's a big difference between a bottle rocket and a Saturn V. And we have to get serious about figuring out how to do that. And the first way to get serious is to talk about your gate errors in a modestly scalable system and know how well you're doing and getting the field to focus on fixing that effectively. Thank you.
I think that what you're saying, John, is actually not it's very much aligned with what Reiner is saying, right? At the end of the day, what we're all looking for is to do something that is reliable enough to create entanglement at large scales, both time and space. And it comes down to putting our efforts to have better control over the systems that we have, and to do it in a way that goes from a single gate to a single gate in a large system to many gates in a large system. And I think we're all working on that. I think there's no question about that. But I think that there's also another point that we need to figure out, which is, what are we going to do with these machines? And I think that it's better to start early than to keep postponing that question. I think another one of our big challenges is start producing results with these machines and start doing some exploration to identify the problems where we see some hints of speed up, and particularly trying to match these things with what people out there are really trying to solve, and move away a little bit from an academic setting to, you know, here's a precursor, if you will, to a quantum computer. What do you want to use it for? So yes, there are incredible scientific explorations that we can do in terms of understanding the underlying principles of these things. There's a lot of science and engineering that needs to go into making these machines larger, better, scalable, robust. But there's also a question of what are the applications that are most promising, both in the near term and that leading into the longer term.
Thank you so much for coming out to our panel today about the 2050 quantum computer. We had a wonderful time stepping out of the usual discussions we have about our current problems and instead looking beyond them and into the future. We have learned a lot, at least I have, and I think we've gained some valuable insight into where the future of quantum computing lies. I think it's an important exercise to try to zoom out a little bit and see the forest and not just the trees. And I hope that you all, the panelists, especially the people watching as well, enjoyed joining us in this panel. And I hope that we have all been able to make some sort of takeaways and to apply them into our current work. And me as a young physicist, and definitely have. And I want to especially give a big thank you to our wonderful panelists for providing such thought-provoking, insightful discussions and really taking it deeply and running with these ideas. We're honored to have you join us today. And on a personal note, I will say that I'm truly awestruck to be surrounded by such true legends in the field. So thank you for your time and your insight and for your true interest in this discussion. And I guess all I can say now is that now that we've talked so much about the 2050 quantum computer, perhaps we should actually try to get there. And I leave that to the new generation, and I mean, of course, you guys and everybody else listening to try to make that happen. So I will just say thanks again, and I hope to see everyone around. And if you guys, the people listening, I'm sorry we didn't really have time for more questions, but if there's any questions, feel free to email us and we'll see what we can do about that.
Thank you.
Thank you very much, Elsie.
Thank you all.
We're on it.
Hey, thank you.
Thanks, everyone.